Hello, I would like to invite you to the presentation of our work titled HALSIE, Hybrid Approach to Learning Segmentation by Simultaneously Exploiting Image and Event Modalities. In this work, we attempt to solve the task of fine-grained semantic segmentation, which consists of assigning a class to every pixel in a given image. Automotive safety systems depend heavily on the semantic information extracted from standard cameras to drive safely in scenarios with other cars and pedestrians. Traditionally, frame-based cameras have been the go-to for semantic prediction. However, they fail to perform efficiently at low latencies due to their dense and redundant outputs at a fixed and low sampling rate. They also suffer from critical issues such as motion blur and temporal aliasing during high-speed motion and are unable to capture meaningful information in challenging lighting scenarios such as high dynamic range and low light scenes. Event cameras, an upcoming sensing modality, eliminates the above issues by asynchronously capturing only the motion information. They do this by monitoring the brightness changes at every pixel asynchronously and independently and generating a binary event if a large enough change is detected in terms of brightness. Event cameras have the potential to improve significantly the robustness of automotive safety systems since they provide low latency and low power measurements which are robust to extreme lighting conditions. The asynchronous and sparse data generated by event-based cameras is not compatible for processing using standard ANNs as they are designed for dense two-dimensional images. In addition, capturing temporal information is essential for semantic prediction but requires the usage of recurrent architectures that are both compute-intensive and difficult to train. Spiky neural networks inspired by the biological brain show promising potential in this aspect. Their sparse asynchronous and event-driven computations over several time steps fit naturally with the event stream generated by these cameras. A spiky neuron can effectively capture input timing information in a state variable known as membrane potential. An output spike is generated when this membrane potential crosses a firing threshold. In the spiky neural model that we use in our work, the membrane potential is also decayed to forget non-essential information, controlled by a dynamic leak factor. Usage of event data with present-day networks requires the events to be accumulated within event bins to form frames. Ideally, we would like to pass the events asynchronously to a network without constructing frames. However, this is limited by the available hardware and learning algorithms. With this in mind, we propose to bring together the best of all worlds. We leverage the complementary temporally sparse but spatially dense frame data and temporal dense but spatially sparse event data to perform sensor fusion for improving semantic performance in challenging conditions. Next, we propose to bring together the complementary spatial and temporal processing capabilities of ANNs and SNNs to design a deep hybrid encoder-decoder network for end-to-end learning. With this in mind, we propose HALSIE, a multimodal hybrid method for efficient semantic segmentation. To efficiently extract rich spatio-temporal features from the complementary sensors, we design a dual-path encoder comprising an ANN-based spatial feature extractor for frames and SNN-based temporal feature extractor for events. The temporal accumulator and multi-scale mixer modules combine these features by a specially designed feature mixing scheme. Finally, the mmix block interfaces with the segmentation head to generate the semantic maps. Next, we evaluate our method on the real-world DDD17, MVSEC, and DSEC-Semantic datasets. The best results are shown in bold and the second best are underlined. Inference energy cost is computed on a standard 45 nanometer CMOS process. We find that our method outperforms other baselines by up to 9% higher MIOU, 77% lower inference energy, and 33 times higher parameter efficiency. Next, we look at some qualitative samples from our method evaluated on the DSEC-Semantic and MVSEC benchmarks. The effectiveness of our method can be verified from the image on the right, where our segmentation results are able to detect very fine details such as the poles or traffic signs, where our contemporaries fail. To investigate the inference energy and parameter efficiency benefits of our method, we plot the segmentation performance versus inference energy on DTT17 dataset evaluated on 45 nanometer CMOS process. The circle areas are proportional to the model size. As can be seen, our lightweight model is the smallest in our comparison with up to 73% lower inference cost than existing approaches. Now, we begin to investigate various ablation insights. We find that HALSIE can efficiently extract information from events and shows promising performance in challenging conditions where fine details are almost invisible in the grayscale frames that are ill exposed, as can be seen in the highlighted colored boxes. Next, we investigate the benefits of sensor fusion. Final objects such as humans or traffic poles highlighted in colored boxes are missing in the predictions made from just events or frames. However, they are detected by a method trained using events plus frames. Next, we explore the benefits of spike processing. We find that SNNs for extracting cues from the input events results in edge discriminative feature maps, as shown in row 2, caused by high spike generation at the object boundary pixels where events are triggered at higher rates. In contrast, using ANN-like dense processing networks as shown in row 3 do not offer similar benefits, with the feature maps looking much fuzzier. Finally, we explored the impact of event window density on performance. Our experiments suggest that maintaining a moderately dense bin with constant event density, as seen in the middle row, shows better semantic performance compared to high density bins with trailing artifact events from fast moving objects in the bottom row, or low density bins with minimal contribution to the segmentation performance, as seen in the top row. At last, we talk about the main takeaways from our work. We introduce HALSIE, a lightweight yet powerful hybrid end-to-end framework for semantic segmentation that is capable of effectively mixing temporal and spatial cues encoded in events and frames. Effectiveness of our design choices is evidenced by the strong performance of our method in detecting finer details on DTT17, MVSEC, and DSEC-Semantic benchmarks while offering sizable benefits in terms of inference cost and parameter efficiency. The resulting design is deployable for resource-constrained edge applications and paves the way for low-energy semantic segmentation with event cameras without compromising on performance. Nonetheless, we hope that this work also inspires novel designs in future hybrid systems. Thank you.